Myself, Dr. Shankaraiah, and Associate Professor in Department of Physics. In this lecture, I am going to discuss about Heisenberg's uncertainty principle. So, before I have discussed about introduction to quantum mechanics, where we have discussed about the failures of classical physics, and then in birth to a quantum mechanics branch, where we learned that radiation is treated as waves in classical physics, but we learned that radiation should also be treated as particles or quanta or photons to explain experimental results like black body radiation, photoelectric effect, and atomic stability. So that is, and later we've also discussed about de Broglie's hypothesis. Not only radiation has the dual nature, but matter also must have this dual nature. That means matter should behave like particles, and matter should also behave like wave. So this wave particle duality must exist both in radiation and matter. So that is what we have discussed in the last lecture. So in this lecture, I am going to discuss about Heisenberg's uncertainty principle. So in the last lecture, we have asked this question: are matter waves harmonic? So so actually, what is a harmonic? Before going to answer this question, are matter waves harmonic? We need to know what is a harmonic wave. So a harmonic wave is characterized by a precise wavelength and constant amplitude. So harmonic wave is a wave that has precise wavelength and constant amplitude. So you can see this here. This wave has precise wavelength. Wavelength is given here. So it is constant. If you keep on drawing this, you will find out that the wavelength is same throughout. And this amplitude also constant. So this is given here, amplitude. This amplitude is also constant throughout. Okay. So harmonic wave is a wave which has constant wavelength as well as constant amplitude. Okay, and it is non-localized and no beginning and no end. You can keep continuing this side, right side and left side, and there is no beginning and no end. It means that such a wave extends over a large volume of space. So this is about harmonic wave. What is a harmonic wave? So can we represent these matter waves by a harmonic wave? So we said that matter waves cannot be represented by a harmonic wave because matter waves do not have a constant wavelength, do not have a constant amplitude. So how are we going to represent these matter waves? So we are going to represent these matter waves by a wave group. Matter waves are represented by wave group. Or group of waves. Okay. So the amplitude of these de Broglie waves that correspond to a moving body reflects the probability that it will be found at a particular place at a particular time. Okay. So we said in the earlier lecture that matter waves are not electromagnetic waves, matter waves are not acoustic waves, but they are a new kind of waves. So these matter waves are actually probability waves. Matter waves are probability waves. Matter waves are probability waves. Okay. So probability waves. So they are going to tell us, suppose if you drop a particle in a box, you are going to ask a question. This is the length of the box A. So you can ask this particle can move freely in this box. You can ask the question, what is the probability of finding the particle at this location, at different locations? So that is what we are going to get from this matter waves. Okay. So that is why we are saying the amplitude of the de Broglie waves that correspond to a moving body reflects the probability that it will be found at a particular time and at a particular place. So it is clear that de Broglie waves cannot be represented by simple wave equation such as y is equal to a cos omega t minus kx, which describes an indefinite series of waves, all with the same amplitude a. It is clear that now matter waves are not cannot be represented by uh, the cannot be represented by harmonic waves. We can represent these matter waves only by wave group, because harmonic waves have constant amplitude and constant wavelength. But we found out that these matter waves are probability waves, so they do not have constant amplitude and they also do not have constant wavelength. That is why we cannot represent matter waves by harmonic waves. We can represent these matter waves by probability waves. So we cannot use the matter waves by this equation y is equal to a cos omega t minus kx. Okay, so we are going to represent matter waves by a wave group. So this is example of wave group picture. So we will see what is this wave group, how do we get this wave group that will be used to represent. Okay, to understand these matter waves, we can consider a simple example that is familiar. We are all familiar with this beats. So we are considering beats as an example to understand this wave group. Okay, so when two sound waves of the same amplitude, this is one wave number 1, and this is wave number 2. So when the two sound waves of the same amplitude, okay, amplitude is same but slightly different frequencies, so the wavelength is slightly different. So if you are going to look at the wavelength is slightly lambda 1 and lambda 2, the wavelength is slightly different but the amplitudes are constant. So a1 is equal to a2, amplitudes are constant, but lambda 1 is not equal to lambda 2. Okay. So the sound which we hear, so we are considering these two sound waves having same amplitude but different frequencies, and the resultant sound which we hear has a frequency equal to the average of two original frequencies, and its amplitude rises and falls periodically. Even though we are considering these two waves are having same wavelength, same amplitude but different wavelengths, we are finding that these resultant wave, third one is a result 1 plus 2 is, we are getting these two waves 1 plus 2 as a resultant wave, and where we find out that the amplitude is not constant. Amplitude here is different from here, so everywhere the amplitude is different, and that is why we are saying that matter waves cannot be represented by these harmonic waves that have constant amplitude and constant wavelength. So to understand that, we have considered these beats where we consider two waves of the same amplitude but different frequencies, and we found out that the resultant wave is having different amplitudes at different positions. Okay, so we can understand this how do we represent a wave group, or what is a wave group, by using this example of beats. Okay, so we are now discussing about wave group, not a single wave. So we need to understand what kind of characteristics this wave group has. So we know that every wave propagates its own velocity called phase velocity. Phase velocity is a velocity of a single or individual wave. Okay. So in a wave group, now we have a single wave, and the velocity of this wave is phase velocity. We are going to say that the phase velocity, there is a single wave and it is going to have a velocity called phase velocity. Now I have a wave group. Suppose I have many waves in the wave group. Okay, if all the waves of the wave group have the same velocities, v1 is equal to v2 is equal to v3. Okay, if all the waves have the same velocities, then we are going to say that this wave group is going to travel with common phase velocity. All the waves in the wave group are going to travel with the same velocity, then it is going to have common phase velocity. However, if the phase velocities varies with the wavelength, The different individual waves do not proceed together, and this is called dispersion. Suppose if the wave group having different waves, and all these waves are having different velocities, okay, different waves have different velocities, then okay, this kind of situation is called dispersion, and the resultant wave is going to have a velocity called group velocity. When all the waves of the wave group have same velocity, then we said that the wave group has a common phase velocity. When all the waves have different velocities, then the resultant wave group is going to have group velocity. So we have discussed what is a phase velocity and what is a group velocity. Okay, so mathematically we can show that here. So to do that, we are considering two waves that have same amplitude but different and angular frequency. Okay, so this is wave 1. Displacement of a first wave is given by y1 is equal to a cos omega t minus kx. Similarly, y2 is equal to a cos omega plus delta omega t minus k plus delta k into x. So this is wave 2. We have considered two waves, and the resultant wave is given by this. Okay, so by adding these two waves, we are getting the resultant wave, and we can write down the phase velocity. So we can write down the phase velocity and group velocity. Okay, so phase velocity is Vp is equal to omega by k, whereas group velocity is d omega by dk. Okay, so this is the phase velocity, and wave velocity we can even derive these equations. Right now we are not going to derive these equations, right? Okay, so now for this we have okay, for this we are going to see what is this Heisenberg uncertainty principle, right? So particle that corresponding to the wave group may be located anywhere within the group at a given time. Okay, so if you have a particle that corresponding to this wave group, this can be located at any point within a group at a given time. Okay, so the probability density is a maximum in the middle. Suppose I have a particle trapped in a box, and you are going to ask what is the probability of finding this particle in a given location. Then we are saying that the probability is going to be maximum in the center, and it is going to decay towards the boundaries to reach zero at the boundaries. Okay, so the probability density is a maximum in the middle of the group, so it is most likely to be found there. Nevertheless, we may still find the particle anywhere that mass I square is not actually 0. So we can find the particle anywhere in this box, but the maximum probability of finding the particle is in the middle of the box. Okay, so suppose if you have a narrow wave packet, narrow wave group, momentum cannot be measured precisely, because here suppose I have a very narrow wave group. This is my wave group associated with the particle, because I have taken a very small box. I have dropped this particle in a very small box, and this is the wave group associated with this particle. For this, I cannot even define lambda. Okay, I cannot define lambda for this. So lambda is we do not know lambda, so we cannot define momentum, because lambda is equal to h by p. If you want momentum, you better have a wavelength, but I don't know what is wavelength, so I don't know what is momentum. But because the region is very small, I can define precisely what is x. So x is precise for a narrow packet. If you have a narrow wave group, very small region of space where you have trapped this particle, you can define position exactly, but momentum not exactly. Okay, so this is where you have a very narrow wave group. Okay, suppose I have another case where I have a wider wave group, right? So in a wider wave group, on the other hand, momentum can be precisely measured, but due to the width, locating particle will be very difficult. This is a wide wave group. Here I can define easily what is wavelength. So wider wave group. lambda can be defined or measured precisely. But now I do not know where the particle is, because this is the location, this is the length of the box. If I suppose this is the whole length of the box, particle can be found anywhere, so I cannot measure what position of the particle precisely. Okay, for a wider wave group, for a narrow wave group, I can measure the position precisely but not the momentum. Here I can measure the momentum precisely for a wider wave group but not the position. I cannot find out, I cannot say where the particle is located. Okay, so using these kind of situations, Heisenberg said that there is uncertainty in finding one of them. Okay, for this kind of particle, so he said it is impossible to know both the exact position and exact momentum of an object at the same time. So this is known as Heisenberg's uncertainty principle. You can measure either position exactly, and then there will be uncertainty in the momentum. You can you can measure the momentum precisely, but then there will be uncertainty in position. Okay, so it is impossible, it's very interesting, but it is impossible to know both exact position and exact momentum at the same time. So this is called as Heisenberg uncertainty principle, and this is the equation. So delta x is the uncertainty in position, where delta p is uncertainty in momentum. Okay, so this is the equal. So both, if you take the product of these uncertainties, it is equal to h by 2 pi, where h is the Planck's constant. So this is called as Heisenberg uncertainty principle. For a classical particle, you can find both position and momentum exactly. So this is very important point. Classical macro particle. Classical means macro. For a macro particle, you can find both x and p exact at same time. Whereas for micro quantum particle or micro particle, this is not true. Not true. That means you cannot find both position and momentum exactly at the same time for a quantum particle. So this is what we have learned in Heisenberg uncertainty principle. So now we want to look at the equation that can be used to study the dynamics of these quantum or microparticles. So that kind of equation is given by Schrodinger. Here we are going to discuss about time independent Schrodinger wave equation. Okay, so we know that in classical mechanics, future history of a particle is completely determined. So this is classical case, you can study the dynamics exactly, whereas in quantum mechanics you cannot study the dynamics exactly. So quantum mechanics also arrives at relationships between observable quantities, but the uncertainty principle suggests that the nature of an observable quantity is different in the atomic realm. So we are saying that the history of a classical particle is exact, but we cannot do so for quantum particle. Okay, so we are defining a quantity called wave function whose variations make up matter waves. To look at these matter waves that are associated with this quantum particle, we need some function, and that function is called wave function. And this wave function is basically quantity. If we look at the variations of these wave functions, and then we will find out the matter waves that are associated with this quantum particle, and we are denoting by psi. The wave function is denoted by psi. So basically this wave function connects the particle nature and its associated wave nature. So we said the matter can have particle nature and wave nature. So here we are saying that this wave function is a function that can connect the particle nature and its associated wave nature. Wave functions are generally complex with both real and imaginary parts. So psi is a plus ib. So a is real and b is here. This part is real and this is imaginary. Okay, so we are defining the wave function as complex quantity, right? And we want to look at the matter waves associated with this particle using this complex quantity, right? So that is the reason why psi itself does not have any physical meaning, because we are defining psi as a complex quantity. Psi is equal to x plus iy. There is a real part and imaginary part, and this will not tell you anything about the probability of finding the particle, or it will not tell you anything about matter waves. That is why psi directly has no physical meaning. The square of its absolute magnitude, which is mod psi square, which is equal to x square minus y square, because a plus b into a plus x plus iy into x minus iy, so that is x square minus y square, so x square plus y square, because I square is minus 1, so that will be plus. Okay, so mod psi square, that is absolute magnitude, square of the absolute magnitude is proportional to the probability of finding the particle. So psi, if you find the psi, you do not get anything because it is complex. But if you can find out this mod psi square, then you can find out the probability of finding this particle. Okay, so it is usually convenient to have mod psi square be equal to probability density p of finding the particle, rather than the merely proportional to p, as particle exists somewhere over time. Okay, so we are defining this integral minus infinity to infinity mod psi square dv must be equal to 1. So this is called as normalization, normalized wave function, or normalization. Okay, so wave function must, if you want to define a wave function, it must satisfy the limitations of the wave function or properties of wave function. We need to know. So wave function must be continuous and it must be single valued everywhere. If you want to define some quantity psi as a wave function, this must be continuous. Wave function must be continuous everywhere, and it must be single valued everywhere. And if you take the derivatives dou psi by dou x, dou psi by dou y, and dou psi by dou z, these derivatives must also be continuous. Derivatives must also be continuous, and they should also be single valued everywhere. Okay, and psi must be normalizable, which means psi must be go to 0 as x goes to plus or minus infinity. If I take a box and psi must be normalized, means that this wave function must vanish at the boundaries plus infinity, minus infinity, or I am taking here this is plus infinity. If I say if it is plus infinity and minus infinity, it must go to 0 at this boundaries of the wave function, so that then we can say that psi is normalizable, or psi is normalized. If psi satisfy this function, that psi goes to 0 when x goes to plus or minus infinity, or y goes to plus or minus infinity, or z goes to plus or minus infinity, in order that the probability density over all space, or probability over all space, is a finite constant. So these are some properties or limitations of wave functions, that you cannot take any function as a wave function. If you want to take any function, if you want to define a wave function, it must be continuous and single valued, its derivatives must be continuous and single valued, and the wave function must be normalizable. Okay, so these are some properties of the wave function. So we have defined what is a wave function and what are the properties of wave function, and now we are going to look into the derivation of this time-independent Schrodinger wave equation. So Schrodinger derived time-dependent wave equation and time-independent wave equation to study the dynamics of these quantum particle or microparticles. In this lecture, in this video, today we are going to discuss only the time-independent wave equation. not the time dependent wave equation. Okay. So if a particle of mass m moving with, so this particle is a quantum particle or microparticle, it has mass m and it is moving with velocity v. So because this is a microparticle, it is going to have associated with a wave group. Okay. So to understand this wave group, we are going to define the wave function psi. Okay. So to understand this, we do not know what kind of wave group or what kind of wave function is associated with this particle priorly. So we are going to say that I'm going to consider a simple progressing wave, simple form of this progressing wave, which is given by this equation. Psi of x is equal to psi naught into sine omega t minus k. So this is what I am defining as a wave function associated with this particle of mass m and velocity v. Okay, so I am going to differentiate this equation twice. So basically I have psi is equal to psi naught sine omega t minus kx. So I am going to differentiate this. So d psi by dx is equal psi naught, derivative of sine is cos omega t minus kx, and differentiation of this minus kx is minus. So basically you have d psi by dx is equal to minus k psi naught cos omega t minus kx. Okay. Now let us differentiate it again. So second differentiation, d square psi by dx square is equal to, so now cos differential is minus sine, so minus will become plus, but then there will be a minus k coming from, so you will get minus k square sine omega t minus kx. So where is psi naught? So we have a psi naught here. Right? So we get the same equation here. So d square psi by dx square is equal to minus k square into psi, because psi naught sine omega t minus kx is psi. So that is why we are writing here is d square psi by dx square plus k square psi is equal to 0. So just do the first differentiation and then again the second differentiation, then you will find out that this d square psi by dx square is basically minus k square psi. So basically find dou square psi by dou x square is equal to minus k square into psi. So that is why I have written this as dou square psi by dou x square plus k square psi is equal to 0. Now here what is k? K is here wave vector. We already know that k is equal to 2 pi by lambda, where lambda is the wavelength. So now we can substitute this k in this equation. So k substitute dou square psi by dou x square plus k square psi is equal to 0. So now we know what is k. So we are going to substitute. So dou square psi by dou x square plus k square is 2 pi by lambda whole square into psi is equal to 0. So that is, so dou square psi by dou x square plus 2 pi square, that means 4 pi square by lambda square into psi is equal to 0. So that is what we have here. Okay. So now we already know that de Broglie wavelength lambda is equal to h by mv. So here we have lambda. So we are going to substitute lambda in this equation. Okay. So lambda is equal to h by mv. So we are going to substitute this h by mv in this equation. Okay, let us see. Lambda is equal to h by mv. We are going to substitute in the equation 4, and then let us do that. So when we substitute this, so basically we have dou square psi by dou x square plus 4 pi square by lambda square into psi is equal to 0. And we are going to substitute lambda is equal to h by mv. So that is dou square psi by dou x square plus 4 pi square by lambda is h by mv whole square into psi is equal to 0. Right? So this is square. So dou square psi by dou x square plus m square b square will go up. So that is 4 pi square m square v square by h square into psi is equal to 0. Okay, we can now, so this is the equation we get here, so that is what we got here. So I'm going to define a new quantity h cut, which is equal to h by 2 pi. Okay, so when I substitute this h cut is equal to h by 2 pi in this equation, what I get is here, because dou square psi by dou x square, h by 2 pi, so this all 4 phi square by h square will go away, it comes as h cut square. So that is why dou square psi by dou x square plus m square v square by h cut square into psi is equal to 0. Okay, this is the equation. So then we know the total energy of a particle is kinetic energy plus potential energy. We know kinetic energy is half mv squared. Potential energy we do not know. We are saying potential energy is given by m just p. Okay, using this equation you can calculate what is m squared. Just multiply by m this equation. This equation, if you multiply by m on both sides, me is equal to m square v square plus m into p, right? So I'm writing m square v square, so 2 will go this side, so 2 me here 2 mv be there, so that is why m square v square 2 m into e minus v. Okay, so this m square v square we are going to place in this equation 6. Okay, substitute this m square v square, which is 2 m into e minus v, in equation 6 and find out the Schrodinger time independent wave equation. Okay, so when we substitute that equation m square v square in equation 6, then we find out dou square psi by dou x square plus 2 m into e minus v by h cut square into psi is equal to 0. So this is the time independent Schrodinger wave equation in one dimension. So this is one spatial dimension. If you have 3 spatial dimensions, this is the Schrodinger wave equation. You can replace this 3 dou square by a del square, which is called Laplacian. So del square psi plus 2m into e minus v by h cut square into psi is equal to 0. So this is the time independent Schrodinger wave equation. So in the next class, we will discuss about the particle in one-dimensional box, trapped in a one-dimensional box, and we will solve this time independent Schrodinger wave equation. Okay, so I'm stopping here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.